from the previous example, you can see that when you have the chemical reaction that have more than one phase of each species that react together, you can choose for the calculation by assuming that the reaction of each species occur in one phase based on maybe gas phase or liquid phase as you prefer. So in the previous example, we start with looking or consider the reaction occur in the gas phase. This one. We start by consider this system has the reaction occur in the gas phase first, and then we use the criteria of the equilibrium, the phase equilibrium to simplify the equation into the each phase that they have to exist in the system. But this is not just one way that you can do when you deal with the heterogeneous reaction. Another method that you can do is you can consider separately for each species in different phases as well. So I said that in mixed state of each species. So for example, you have the same reaction of the A in the gas phase react with the B in the liquid phase. Then you get the C species in the aqueous. Aqueous is a mixture when you have the solute and solvent, right? When you have solute and solvent, then it calls aqueous. So in this case, you can also consider the reaction that occur at the equilibrium based on the mixed state of each species. For example, the equilibrium constant can be evaluated based on the mixed standard state of the A. Standard state of the A in the gas phase is the pure ideal gas, which is equal 1 bar. So the viscosity at the standard state is equal to the standard state ratio. The B is in the liquid phase, so the standard state of the liquid phase is the pure liquid at 1 bar, just pure liquid. So the C, standard state of the C, which is aqueous, C is the solute in solution, right? It's called aqueous. So the C, the standard state of the solute, is the ideal molar aqueous solution. This is mean the concentration is the unit of the concentration. It is the molarity, if you remember. So what I just want to say is the standard of the solute component is the one molarity of the solute itself. So for example, you have the equation of the chemical reaction equilibrium like this. Then instead of considering that each species occur in the vapor phase, every species exist in the or react in the vapor phase, you can consider that each species react in the that species itself, that phase of the species itself. Example, the ratio or the fraction of the viscosity of the species B and species C in the aqueous phase, right? For species B in the liquid phase, for the A species is in the gas phase, like this. Just different for each species. And then you can simplify this equation based on the phase of each species itself. For example, in the case of the aqueous here, species C, the viscosity of solute in the solution over or divided by the viscosity at the standard state of species aqueous here is equal to the molarity or the concentration of solution. I will explain this in the next slide. But for the liquid here, you just change the viscosity of species B in solution to the activity coefficient times with the mole fraction of B in liquid phase and come with the frequency of the pure species over with the standard state frequency of the species. I actually change the I symbol here to the substitute U, which is actually equal. And for the gas phase, you just change for the standard state frequency of the gas phase is equal to the standard state ratio. You can do this way as well, but from my experience, I recommend you start with the considering every species in one phase first. For example, in the previous example that you considering that every species react in the vapor gas phase first. Then you just use the criterion of the phase equilibrium to change the frequency of one phase into another phase that of that species to base. In that way, it will be more less complicated and easier to understand. But I just want to show you that you can do another way as well. And for the fraction of the frequency of species in the aqueous over with the frequency at the standard state in the aqueous equal to the molarity of the species. This comes from the Henry's law. So the Henry law is used to assume the standard state for the solutes. The Henry law is here. As from the equation here is the frequency of species I in aqueous equal to the Henry law constant, which is the small letter k here, with subscript of the capital H is from Henry, and I is for species I. And it comes with the M with subscript I here is, and you have another symbol as the superscript here, is the molarity or it is the solute concentration. And the unit of the molarity usually is the mole of solute over kilogram of solute is the unit of molarity. And from this equation, so Henry law actually can be plotted at the state line when you plot between the relation of the frequency of the species in aqueous versus with the molarity of the solute or the concentration of the solute. You can get the state line of the Henry law with the slope of the Henry law constant. So in this case, if the actual concentration of species when you plot between the frequency and molarity and the concentration is close to approach to zero like this, usually the Henry law can be applied to the concentration to the standard state of the concentration. And in that case, it means that standard state frequency based on the Henry law should be equal 1 molarity. And from this equation, at the standard state, I have changed the superscript here into the degree symbol here. So it means the standard state frequency will be equal the constant of the Henry law. So in that case, in the final, you can get a fraction of the frequency in solution over the standard state frequency equal to the molarity that I have shown you in the previous slides. So this is the explanation of how to change the fraction of frequency over the standard state frequency in the case that you consider the species is in aqueous phase. Yeah, but as I said, usually I recommend to start with maybe every species react in gases or every species react in only liquid phase and just use the phase equilibrium criteria to change the form of the frequency for each species. Okay. The remaining content that we have to go through is the chemical reaction for when you have multi-reaction system. So if you notice, so far we just see an example that we have only one chemical reaction in the system, just one chemical reaction. But what happened or what changed to the calculation when you have more than one chemical reaction in the system? So first, I just want to explain the phase rule for the reacting system first. As you might have known that normally the equation for determining the degree of freedom, the F here is the degree of freedom. Usually is equal to number 2 minus with the number of the steps with the pi symbol here. The pi symbol is number of steps in the system. Plus with the n. N here is number of chemical species. This is usually the general equation for determining the degrees of freedom. But in the case that you have the reaction, chemical reaction in the system as well, you might have another two parameters to use to calculate the degree of freedom as well. In this case, you have to minus the number of the chemical reaction that have in the system, and also another constraint. Here the S here is the number of equations from the spatial constraint. So S is come from spatial constraint. The example is, for example, you have one system and you have two species which is does not react together. Two species and not react together exist in the vapor liquid equilibrium. So two phases, right? Vapor liquid equilibrium, two phases. So how many of the degree of freedom in this system? So let's first start. If there is no azeotrope, we just neglect at first that there is azeotrope. The degrees of freedom should be equal to 2 minus 2, which is come from the number of the steps, which is vapor and liquid is in equilibrium, and plus with the number of species, which in this case is 2 species, and the 2 species does not react together, non-reacting species. So for the number of the chemical reaction is equal to 1. So in this case, the degrees of freedom equal to number 2. But what if you have another spatial constraint in the system, which is azeotrope in the system? The azeotrope is the point that the curve of the bubble points and dew points touch together. So at this point, you can see that usually if you have the mole fraction that exists inside the envelope between the curve of the bubble point and the point here, you can draw the tie line, right, to cut with the curve of the bubble point and dew point, and then you can determine the mole fraction in the vapor phase and liquid phase. But in the case that the mole fraction at the azeotrope, you can see at this point, you cannot draw the tie line. It's just a point. So the meaning of the azeotrope point here is the point that the mole fraction of the mixture system that you have the mole fraction in both vapor and liquid phase is equal together. In the mathematics, it's the yi equal xi. So in this case, if we consider back into the degrees of freedom, the azeotrope is come from, in this case, it is a special constant to uh, have to consider to calculate the unknown parameter in the system. So in this case, when you calculate the degrees of freedom here, you have another one equation or one constant. In this case, is the x1 equal y1. Yeah, in this case, x1 equal y1. Another equation that you can use to calculate the unknown parameter. So in this case, the degree of freedom is equal 1. It means that the meaning of the degrees of freedom is useful when you have a very complicated system and you want to know that how you can fix the unknown, the parameter, how many parameters that you have to fix the system to get into the considering system that you want. So in this case, the degree of freedom is equal 1. It means that if you fix the temperature here, for example, in this graph is 101.3 kilopascal here, then another parameter will be fixed with fixed pressure here. For example, the azeotrope of two non-reacting species will be only at this temperature only. So it's maybe 75, for example, maybe 75. If you can fix the system by fixing only one parameter, in this case is pressure. So if you fix pressure, you can fix the temperature of the system. For example, in this, when you have the spatial constraint with this CO2. But in the case that you don't add the spatial constraint, as in the isotope here, you can see that if you fix the temperature, fix the pressure, and we want to talk that to fix the same point together, we have to say that which temperature that we talk about. So the Weber liquid equilibrium should be in the envelope, right? But which point? So we have to pick another parameter. In this case, is the temperature. Then we can say that it is the same point that we talking together. That is the meaning of the degree of freedom. So in the case that we have the chemical reaction, what happens with the degree of freedom? For example, is you have the system that occur that the reaction of the decomposing of the calcium carbonate occur in the system. So you have the calcium carbonate here, which usually is in the solid form, the white powder here, the calcium carbonate. It's decomposed into the calcium oxide. It is in the solid form as well, and carbon dioxide. So in this case, how many of the degrees of freedom here? You can calculate directly. This one, you have 3 phases. Do you confuse why do you have 3 phases? You have solid and gas. Why do you have 3 phases, not 2 phases? Isn't just 2 phases? It's a solid and gas. This is wrong. Actually, it's correct. It is 3 phases because the solid phase should be separate together. You have the solid phase of the calcium carbonate, and you have another solid phase of the calcium oxide, and you have another phase of the calcium carbon dioxide. So in this system, you have 2 phases, not 2 phases. So 2 minus 3 phases plus with 3 components, 3 species, and minus with 1 reaction. So in this case, and no constraint different. So you have 1 degree of freedom in the system. It means that, as I said, I try to explain the meaning of the equilibrium. So it means that if you fix pressure already at a certain pressure, the calcium carbonate will be decomposed at the fixed temperature because you have only one equilibrium. If you have